what are we going to talk about? So on the Commodore, can you hear that? You set the sound with the frequency. I want every kid in America to do a for loop I want every kid in America to do a for loop 1 millisecond. Well, I think we need this. Every kid in America needs to do a police siren. So how do you do a police siren? Siren. Every kid, black and white. You know what, actually, so if you're doing this and you change your mind, Control Shift L, reindent, and anyway, so this is going to go up and down. Oh, I didn't. We have to say siren. What if we go to the command line, include it, and say siren? Now VMware put distortion, ridiculous distortion. One of my demands is that they fix it. Here's what QEMU doesn't have any distortion, and it sounds bad for special effects. If you're making explosions, you want distortion. Anyway, I wish they would just do it like a real speaker. A real speaker, I have a computer that it works on. It's got just the right amount of distortion. And anyway, but you might as well make it adjustable. No, don't make it adjustable. Well, anyway, add reverb when you're doing VMware. VMware is the virtual machine I use. Anyway, I use Linux and I run this in VMware. Okay, so I can hit, you can hit F5 is the IDE. Oops. There's a mute. I think Control-Alt-M. Control-Alt-Shift-M. Oh, Control. I guess it kills it. I don't know. Let's find out what it does. Control-Alt-M. Toggle mute. What does mute do? Control-Shift-F1. Up. That didn't work. Control-Shift-F1. Mute. As a matter of fact, I got rid of preemption, but I did not fix the code. The reason it has these instructions turn off interrupts. This was a precaution against another task doing a sound operation before we're done. Even that doesn't make sense. That doesn't really make any sense, does it? I don't think it makes any sense. I don't think that makes any sense. Why did I do that? Normally you have a you want to make it atomic. Anyway, for some reason I felt that was good. So it does a sound 0. Okay, well anyway, I'm kind of embarrassed. I have to think really hard about what that should be. I have to decide if we really are never going to have preemption. I removed preemption. The reason I removed preemption, let me explain. Like if we have a committee of my peers, so task grip. So what we have is a round-robin scheduler. Each core keeps the tasks located on that core. It doesn't ever move them around. Core 0 is where the applications run. They start, and then they can call slaves on the other cores. Core 0, this has children task of Adam. And I think these are children of Adam too, but oh well. Anyway, the window manager task draws the screen 30 times a second with a callback. So here's why I got rid of preemption. I found myself, so there's a draw. Let's look for another example. Where's mass spring? Didn't I do mass? What about doodle? No, not doodle. Mass spring is up here. Mass spring. Okay, so here we have random masses, and if you right click, it puts springs between them. This is mass springs. So mass springs. Anyway, so if we look at this code, it's storing. Well, you know, that really is nasty for kids. Anyway, it's using a base class. You have to look it up, and it has a queue. And you know, that wasn't even it. That wasn't it. Okay, anyway. So a circular doubly linked list is how we do everything. And if you let's explain what a circular doubly linked list is. I'm going to do so. Oh no, we want a text box. So you can do documentation. in your code, maybe you want to so I used to call them roots, but anyway, it's a head. Now we're going to do arrows. So what a circular doubly linked list is, these are pointers and these are little chunks of memory. The reason we do them like this is because you can remove them without any problem. It's really easy to remove and it's pretty easy to insert. Once you learn the basics of how you work with these, you can just always use them. Now, a young person might say, yeah, but I only need one linked list. I just need a linked list. And I'll put a pointer to the end. Well, guess what? Now you have to think about it. If you just do it this way, you don't have to think about it. Now, I don't really like the STL. That's gone way beyond pleasant. They got iterators and crazy shit. Anyway, so with a linked list, let's say you're doing a new mass and you're going to put it in here. You have to break these pointers and put a new mass in there. And guess what? As you're working, the window manager is drawing all these masses. The window manager is going in a circle. Oops, you just broke a link, and you know, maybe you did it safely, but maybe you did not do it safely. What if you deleted something and you weren't paying attention? Sometimes they can make, if you do the order right, you can get this without causing problems, but that's too hard to think about. So what you just do is turn off. You don't want to be interrupted. If that task is going around doing this and you decide to delete, now you got a problem. So what I did is I got rid of preemption. Now let me explain what that protects you against. What that means is, if you decide to go in there and delete, it's not going to interrupt you while you're doing it. So you're going to be able to successfully delete this, and then maybe the window manager will run. So it's kind of tricky. You only yield when you want to yield. So when are we yielding? Well, this has a main task, and then you'll see it has a, no, this doesn't. Normally we make song tasks and we make animation tasks. This has a main task, and here it's getting a message, and what it does is it yields until a message arrives. So this goes to sleep until a message. And so if we get a message, then we get the CPU and nobody interrupts us. And we place a new spring and we break the links to make our new spring. And it's okay, it can call that, and it'll break Q insert is the no-brainer way to you insert the predecessor, you insert You insert this pointer to a node after the predecessor. Anyway, once you get the study it, insert, remove, init. Now it gets tricky if you have two sets of Q links. Anyway, one of the reasons I only allow one base class is because the compiler doesn't really tell you how it's going to organize it if you have multiple base classes. At least I don't understand. Anyway, with one base class, it's clear that it's the one that, anyway, so long story short, it does not preempt you, so you can break these links and add another one in, and the window manager task will not run while you're doing it. Now, you have to be careful, because after I said that, what about these other cores? Holy shit. If those cores are accessing it, now you got a problem, because there's nothing stopping them. So that's your problem. Now it's your problem. So you have to set up a lock or something like that. And what I do is a yield on a lock. I do a bit. There's a, if you do F1, these are bit operations that are locked. The bus, the computer bus is locked. And so, long story short, that makes it safe for multi-core. So you can lock. This is an atomic lock, bit test and set, bit test and reset. You know, they don't teach this. Nobody uses this. This is what I learned at Ticketmaster: bit test and set, bit test and reset. They're doing something that's not as good. So in order to do, so I spin on a lock. However, I am in a different situation. Well, true. So, guess what? I am saving my context of registers and restoring the next context to registers. I'm doing that 4 million times a second. Nobody else can do it this fast because I'm using the same address map. I don't mess with the page tables, and all I'm doing is doing the registers. So my spinning is really, really fast. And we're making a toy that's not a server. We are not planning on having 100 users. If you had 100 users and it went around in a circle, now you're starting to waste a lot. But we're only going to have a maximum, 10 tasks or something. How much do you need for a video game? As a matter of fact, I said I cherry pick. The way I don't want to do everything Linux can do. I want to leave Linux with the server business and stuff like that. What our business is Commodore 64 games. We want to serve user developers making games. So your little kid can make Donkey Kong instead of playing first-person shooters, because that's kind of what do is play first-person shooters. Little white kids, they actually like to program. That's why Minecraft, it's really sad they have Minecraft. That's not that's pathetic. That brings a tear to your eye, doesn't it? The poor kids doing shit in there. They need a good toy. Anyway, so we cherry pick. So we're not going to do 100 tasks. If we want a lock bit, we're going to spin on a lock bit. And when you yield, it's not the same as blocking. Isn't that the technical term, blocking? If you block, then you use up all the CPU. But when we spin, we don't actually use up the CPU. We yield to the next task. It will max out the CPU, but it's not a problem. I can actually yield tasks faster than I can read a bit. So when we're waiting on disk, what we're doing is yield. So let's analyze this. So you have one task that's waiting on a disk. It reads a port, that's half a microsecond, and then it yields. That's another quarter microsecond. And then it swaps in the next task. There's 4 or 5 tasks. Maybe they're all waiting. So it spins around pretty quickly. And maybe the hardware becomes available in 2 microseconds. We didn't waste that much time. It works pretty well. Now, what you'll notice pretty quickly is I don't break disk requests in pieces. So, for example, there's a big. This is the only place you'll notice it, but you'll really notice it if it's a slow computer or a. The only big file I have is my dictionary definitions. We actually have definitions of English words. Control-Shift-0. So it's got a full dictionary. That's why it's so big. It would only be 2 meg if we, or 4 meg if we didn't, or 6 meg anyway. But we want a dictionary because, well, I don't know. I want a better one. But anyway, so what was I talking about? So we don't break disk requests in pieces. So if you copy this to a compressed or an uncompressed, I think it's 20. How many meg is this? I don't know. (16), 25 meg uncompressed. It's going to use the CPU. It's going to take a couple seconds. And nobody else can use the disk while it's doing it. And that's why I call this sometimes I call this single process multi-thread. Because we don't have sharing, we are not really equipped to have 100 users because we don't have sharing. We don't evenly balance the disk. If one guy hogs it, it's not equipped to handle that. What we're in the business of doing is one user playing one video game. We don't do 2 video games at once. It's mostly for one process. But you know what? We want you might say, why don't you just do it like DOS and have it single task? Well, there's some advantages to having multitasking. You can do songs. Songs are really easy when you have multi-thread. We have single process multi-thread. I think that's the best way to describe it. The goal is what a Commodore 64 was used for. If you want to know, here's what I'll tell you. It's designed for these 20 applications, no more and no less. And it works marvelously doing these. Okay, that's what I'm going to tell you. If you tell me, oh, it doesn't do this, I'm going to tell you we cherry-picked these applications and this is what it's for. So, as I like to say, some people want to move heaven and earth so that you can play 2 video games at once. But we're not that stupid. We're not going to go out of our way to play 2 video games at once. We're going to make it awesome. So I don't share the disk. So there's a lot of operating system theory that I just dodged. mine, it's kind of like talking about operating system theory with DOS. DOS really doesn't involve much operating system theory. Anyway, the fun things are, you know, I do have a disk cache. One time I got a rude awakening when I tried doing a write cache because I had a deadlock. And that was the first time I encountered two fighting for the same resource. You know what I did? I got rid of write cache. And now I don't have any situations where there's any complicated theory. It's just really simple. It's like DOS. DOS has no operating system theory. So I'm kind of proud of that. Anyway, so now you might ask why. Now the callback doing the screen update presents a problem for debugging. This is bad, but that's the way it is. So there's a few bad things. You can't grow the stack. It doesn't use paging, so you need a fixed stack. And if it's a fixed stack, it might as well be, I think I have 256K or 128K for the stack. You know, if you add more, it's never going to be enough. So you might as well just leave it modest. So that's a problem. So you can't do a crazy lopsided binary tree. That's going to cause a problem. So that's the worst. That's the thing I hate the most, or I most regret. But multitasking for the window manager updating with a callback is pretty nasty for debugging. So when you start setting breakpoints, you can say debug, and you can set a breakpoint. Go. Nobody's going to use the debugger, and I'll tell you why. Because it's too hard to use. Here's what you need to know about the debugger. Is there a breakpoint? I could swear there's a... that's not what we want. Oh, well. Why isn't that an instruction? Oh, it's interrupt 3? Isn't that what it is? Why don't we have an alias for breakpoint? I think it's interrupt 3. CC or something. Control interrupt. Interrupt 3, interrupt. Oh, interrupt 3. Well, isn't that? But why don't I make an alias? You think I should do that? I think we should do that. How do I make an alias? I forgot. I think all I do is I say breakpoint. Ah, fuck. Let's look. Control F, jump greater equal. Jump greater equal. There. At the end I say colon alias. Okay. At the end I say colon alias. Okay. Control F, interrupt 3. Well, that's kind of funky. Colon breakpoint. I have a song. Done, I'm done, and I'm on to the next one. Done, done, on to the next one. Okay. Okay. Escape. We reboot. I hate when that happens. Ah, shut up. Done, I'm done, and I'm on to the next one. Okay. Son of a bitch. Okay. So when the compiler gets initialized, it loads the opcode file. And I can't tell, was it parsing the opcode file, or was it, I don't have breakpoint somewhere, do I? Find breakpoint? I don't think so. We don't have breakpoint. Find breakpoint. Don't ignore case, and find an isolated word. Find a label. Okay, that's what I thought. No, it's not. Okay, let's look for the colon. Oh, it's... I think we need a none. And then a colon. It might be looking for arguments. I don't know. That's fucked up. What is your malfunction? Maybe a comma? You think it needs a comma? That might do it. There's no particular this file is entirely my own creation, and whatever rules I make are, that's better. Okay, so it needed that comma. Okay, there's actually a flaw in the grammar of that file that I just recently discovered, but the flaw doesn't happen, so we're okay. Okay, so we want to put a breakpoint. How about right here? BPT. You can mix assembly and C. I know that sounds incredible, but if it sees an opcode, it codes assembly. So you can mix assembly and C. It's the best compiler ever written. And let's go ahead and okay, so we executed it, it hit the breakpoint. So now what do? I suggest we change it to a no-op. What is that, 90? So single step. Oh, not capital. Single step. Oh, the breakpoint. We have to skip it. You think we can advance it? See, it's not really set to remove that breakpoint. RIP plus plus. Go. Okay. Underscore RIP plus plus. Go. So it is doing it. Now we say exit G2. I knew that. Exit kills the task. So here's the main thing. When you get in the debugger, look at the stack trace. That's the most valuable thing. The RIP at the beginning is valuable. The stack trace is valuable. And then you should probably type exit to kill the task. If it's the window manager task and you hit exit to kill it, your system's crashed. So if it's a window manager task, don't even bother to hit exit because it's hosed. Now, if you want to set a breakpoint the normal way, So let's say you wanted to do this conventionally. So you unassemble function siren. You set a breakpoint, address siren plus 0x. What do we want? 32? Now we say go. You don't say go, you say siren. Now what this does is it says call siren. Okay, now these breakpoints we can single step, I think, and then you say go. This will remove it and go. Okay. So we can say breakpoint remove. How do we do that? I don't remember. How about breakpoint address RIP? I wonder what that'll do. Not address RIP. I don't know if it toggles them. I don't remember, to be honest. Go. Okay. Now if you want to enter the debugger, Control-Alt-D. Control-Alt, no, is that how you do it? Control-Alt-D? Control-Alt-D is in the interrupt routine, and it enters the debugger. Let's unassemble RIP. We are crazy. Where are we? I don't even know where we are. We could look at the stack rep, caller rep. I think there might be a caller rep. So we executed, I think this is the idle task. I don't know, whatever. Let's just say go again. And we are hosed. I don't know. So maybe we get a committee and I get a little bit of help, but I have the last word, and it's divine intellect. And